We are watching scientists quietly panic. Not on the news. Not in some dramatic press conference. In the pages of peer-reviewed journals, in conference talks, in the careful, hedge-filled language astrophysicists use when they don't want to admit something is wrong, but can't hide it anymore. The James Webb Space Telescope was supposed to confirm what we already believed about the birth of the universe. Instead, it pointed its mirror into the deepest, oldest light we can see, light that has been traveling toward us for over 13 billion years, and found something that, according to the textbooks, should not be there. Fully formed galaxies. Massive, structured, glowing with the light of countless stars. Sitting in a part of the universe that was supposed to be almost empty, a cosmic nursery, not a cosmic metropolis. If the standard timeline of the universe is right, these galaxies are impossible. And scientists don't like the word impossible. Because it usually means one of two things: either the observation is wrong, or the theory is. This time, the observation keeps checking out. So stay with me, because we're about to walk through exactly what JWST found, why it's shaking the foundation of modern cosmology, and what scientists are now proposing might have really happened, in the first second of time. To understand why this discovery is such a big deal, you need to understand what astronomers expected to find, before JWST ever launched. For decades, our best model of the universe, called the Lambda-CDM model, where Lambda stands for dark energy and CDM stands for cold dark matter, has predicted a slow, patient universe. In this picture, right after the Big Bang, the cosmos was a hot, dense soup of particles. As it expanded and cooled, gravity slowly pulled matter together into clumps. Those clumps pulled in more gas. Stars formed. Small galaxies merged with other small galaxies. Over hundreds of millions, even billions of years, those small galaxies gradually built themselves into the massive, mature structures we see around us today, including our own Milky Way. It's a model built on patience. Small things first. Big things later. That's the rule. JWST was built specifically to test this rule, because unlike any telescope before it, JWST can see in infrared light. And infrared light matters here, for a very specific reason. As the universe expands, light from extremely distant, extremely old galaxies gets stretched out, a phenomenon called redshift. Visible light from the earliest galaxies has been stretched so much by billions of years of cosmic expansion that, by the time it reaches us, it's no longer visible light at all. It's infrared. Hubble, JWST's predecessor, was mostly blind to this ancient infrared glow. JWST was engineered to see exactly that. So when JWST turned its gaze toward what astronomers call the deep field, patches of sky that appear almost completely dark because the light took so long to arrive, it wasn't expecting much. Faint smudges, maybe. Small, chaotic blobs of gas, just beginning to form the first clumsy stars. That was the prediction. What it found instead were galaxies. Not smudges. Not blobs. Actual galaxies, with structure, with mass, some even showing hints of the disk shapes we associate with mature, settled systems like our own. And these galaxies weren't sitting comfortably a few billion years after the Big Bang, where the standard model says structure formation should already be well underway. Some of them were sitting at redshifts corresponding to just a few 100 million years after the Big Bang, cosmic infancy, on a timescale where the universe had barely had time to cool down, let alone build cities of stars. One of the most famous examples is a galaxy called GN-z11, confirmed spectroscopically as existing roughly 430 million years after the Big Bang. Multiple other candidate galaxies have been identified even earlier than that, some pushing toward the 300 million year mark, and a few contested candidates edging even closer to the beginning of time itself. Researchers studying these objects have openly described finding a surprising excess of luminous galaxies, far earlier than models predicted, not a handful of outliers, but a consistent, repeated pattern across multiple independent surveys. And it's not just that these galaxies exist too early. It's that some of them appear too big, too early. Analyses of their brightness suggest stellar masses that, in some cases, push uncomfortably close to, or even beyond, the total amount of ordinary matter that should have been available inside their dark matter halos, at that point in cosmic history. In plain terms, some of these galaxies may contain more stars than there should have been raw material to build them from, given how young the universe was when they formed. Then there's the chemistry problem. When astronomers examine the light from some of these early galaxies, they don't just see hydrogen and helium, the primordial elements forged in the Big Bang itself. They see heavier elements, oxygen, carbon, sometimes even iron. Elements like these are not created in the Big Bang. They are forged inside the cores of stars, and then scattered into space when those stars die, often in supernova explosions. Finding meaningful amounts of these heavier elements in galaxies from the universe's earliest few 100 million years implies that entire generations of stars had already been born, lived, and died, recycling their material into the next generation, in a fraction of the time the standard model allows for even one generation to complete its life cycle. Put simply, JWST isn't just showing us galaxies that formed early. It's showing us galaxies that appear to have already lived a full, rich history, one that, by the old rulebook, shouldn't have had time to happen yet. None of this came from a single lucky snapshot, either. Some of the strongest evidence has come from large, dedicated survey programs, projects like CRS, JADES, and GLASS, where teams of astronomers pointed JWST at the same patches of sky for extended periods, layering exposure after exposure to pull out the faintest, oldest light possible. These aren't quick glances, they're methodical, years-long efforts involving dozens of researchers cross-checking each other's results, which is exactly why the early galaxy findings have held up as well as they have. When one team's data is independently confirmed by a completely different survey using different instruments and different analysis methods, that's when a strange result stops being a curiosity, and starts being a genuine scientific problem. One of the most striking record holders to come out of this effort is a galaxy known as JADES-GS-z14-0, identified through the JADES survey and later confirmed spectroscopically as existing only around 290 to 300 million years after the Big Bang, making it, at the time of its discovery, one of the most distant, and therefore one of the earliest, galaxies humanity had ever confirmed. What stunned researchers wasn't just its age. It was its brightness. A galaxy that young should be small and faint, barely scraping together its first few clusters of stars. Instead, JADES-GS-z14-0 turned out to be unexpectedly luminous and surprisingly large for something that formed so close to the very beginning of cosmic time, bright enough that some astronomers openly admitted they didn't expect to find something like it until much later observing campaigns, if at all. This is the pattern that keeps repeating, not one exceptional galaxy, but a growing catalog of them, spread across independent surveys, each one adding another data point to a picture that the old model simply didn't predict. This is the discovery that's forcing astronomers to ask an uncomfortable question: what if we've been wrong about how fast the universe was able to build itself? Here's where it gets serious, because this isn't a fringe idea, or a single controversial paper. This tension between observation and theory has now shown up across multiple independent JWST surveys, multiple research teams, and multiple methods of measurement, and it hasn't gone away with more data. If anything, it's gotten sharper. The Lambda-CDM model isn't just a rough sketch, it's the product of decades of work, and it explains an enormous amount about the universe correctly, from the leftover glow of the Big Bang itself, known as the cosmic microwave background, to the large-scale web of galaxies stretched across the cosmos. This is important to say clearly: nobody serious is throwing the entire model in the trash. What's happening is narrower, but still deeply significant. The model's predictions about exactly how quickly the first massive galaxies could form are running into a wall. One of the clearest voices on this tension has been astrophysicist Michael Boylan-Colchin, whose analysis of the earliest JWST galaxy candidates showed that several of them would require an almost impossibly efficient conversion of raw gas into stars, efficiencies that bump against, or in some interpretations exceed, the physical limits astronomers thought applied in the early universe. Other researchers have echoed this, describing the number and mass of these early bright galaxies as being in real tension with the majority of pre-JWST theoretical models. To be fair to the skeptics, and good science requires being fair to the skeptics, some of this tension may have mundane explanations. Measuring the mass and age of a galaxy that is barely more than a smudge of pixels, whose light has been traveling for over 13 billion years, is incredibly difficult. Some early, impossible, galaxy candidates have later been reclassified as much closer, much more ordinary objects, once better spectroscopic data came in, a reminder that photometric redshift estimates, the quick method of guessing a galaxy's distance and age from its color, can sometimes fool us. A few of the most extreme claims from the first years of JWST data didn't hold up under closer scrutiny. But even accounting for that healthy skepticism, a meaningful population of confirmed, spectroscopically verified galaxies remains, genuinely early, genuinely massive, genuinely hard to explain. The problem hasn't been explained away. It's been narrowed down and made more precise, and it's still there. There's also a second, related crack in the standard model worth mentioning, because the two problems keep showing up together in the scientific literature: the Hubble tension. This is a long-running disagreement over the exact rate at which the universe is expanding today, called the Hubble constant. When astronomers measure this rate using nearby stars and supernovae, they get one number. When they calculate it using the cosmic microwave background, the faint afterglow of the Big Bang itself, they get a noticeably different number. Both methods are precise. Both teams have checked their work repeatedly. And yet, the numbers still don't agree. For years, this was treated as a separate, somewhat contained puzzle. Now, some cosmologists suspect the Hubble tension and the galaxies grew up too fast problem might be two symptoms of the same underlying issue, some overlooked piece of physics operating in the early universe that current models simply don't account for. That's not proven. But the fact that two independent anomalies are pointing theorists toward the same suspect, the physics of the universe's first moments, is part of why this issue is being taken so seriously. So what could actually be going on? Broadly, researchers have converged on a handful of serious candidate explanations, and it's worth walking through them honestly, rather than picking the most dramatic one and running with it. The first possibility is star formation happened in short, violent bursts, rather than the smooth, steady process the old models assumed. If early galaxies didn't form stars gradually, but instead went through rapid, intense bursts of star birth, flaring brightly, then dimming, then flaring again, they could appear far more luminous at any given snapshot in time than a steady-state model would predict, creating an illusion of being more massive than they actually are. This is sometimes called bursty star formation, and there is growing observational support for it. The second possibility is that the earliest generations of stars were fundamentally different from stars today, larger, hotter, and more efficient at converting gas into light, sometimes referred to as a top-heavy initial mass function. If the very first stars skewed toward giant, blazingly bright stars, rather than the more modest mix we see in galaxies today, fewer stars could produce far more light, again making young galaxies look deceptively massive. The third possibility is the most unsettling one, that our cosmological model itself needs a modification, particularly around how quickly matter was able to clump together in the universe's first moments. This is where things start to touch, the first second of time. Every cosmological story begins in the same place, an unimaginably brief, violent period at the very start of the universe, often called cosmic inflation, followed by a longer era of expansion and cooling governed by the balance of gravity, radiation, matter, and a mysterious force called dark energy. Here's the thing that makes this early galaxy puzzle so interesting to physicists specifically: it isn't only an astronomy problem. It's potentially a fundamental physics problem, because the rate at which structure could form in the early universe is directly tied to the physical conditions that existed in that first sliver of a second, the strength of dark energy, the exact behavior of gravity at that time, and how matter was distributed just after inflation ended. One of the more serious proposals circulating in cosmology right now is the idea of early dark energy, the hypothesis that dark energy, the mysterious force responsible for the universe's accelerating expansion today, may have behaved differently, and been temporarily stronger, in the universe's first fraction of a second than it is now. Interestingly, this idea wasn't originally invented to explain JWST's early galaxies at all. It was proposed years earlier as one possible fix for a separate, long-standing puzzle in cosmology known as the Hubble tension, a persistent disagreement between different methods of measuring how fast the universe is expanding today. It's a genuinely open and actively debated area of theoretical physics, not a fringe idea, but it's also far from proven, and plenty of cosmologists remain unconvinced it's necessary. What would it mean if early dark energy, or some similar modification to how gravity and expansion behaved right after the Big Bang, turned out to be real? It would mean gravity had a head start. If the tug-of-war between the outward push of cosmic expansion and the inward pull of gravity tilted differently in that first second than our models assume, matter could have started clumping into stars and galaxies earlier and faster than the standard timeline allows, which is exactly the kind of head start that would be needed to explain galaxies that look far too mature for their age. It's worth being honest here, this remains a hypothesis, one of several competing on the table, not a settled conclusion. Cosmologists are actively testing it against multiple independent lines of evidence, not just early galaxies, but also the pattern of ripples in the cosmic microwave background and the large-scale clustering of galaxies across the universe. So far, no single explanation has cleanly solved every piece of the puzzle at once. But the fact that mainstream, credentialed physicists are seriously entertaining the idea that the physics of the first second of cosmic time might need revision, that alone tells you how significant this moment is for the field. While theorists have been wrestling with dark energy and inflation, observers have stumbled onto something else entirely, something that might be an even bigger piece of this puzzle. It has to do with a strange population of objects JWST keeps finding buried inside, or right next to, these early galaxies, tiny, intensely red points of light that astronomers have started calling, almost affectionately, little red dots. These little red dots were a genuine surprise. JWST started spotting them almost as soon as it began operating, scattered across the deep field images by the hundreds. At first, some scientists assumed they might simply be small, mature, dusty galaxies. Dust tends to redden light, the same way smoke reddens a sunset. But there was a problem: these objects were far too compact. Some are estimated to be smaller than 2% of the diameter of the Milky Way, yet they're pumping out an enormous amount of light for their size. Packing that much brightness into that little space using ordinary starlight alone would require a density of stars so extreme it strains belief. The leading explanation gaining traction now is that many of these little red dots aren't simply young galaxies at all, they may be a genuinely new category of object, centered on a rapidly growing supermassive black hole. Some researchers have started calling them black hole stars, a colossal, glowing envelope of hot gas, larger than our entire solar system, powered not by nuclear fusion like an ordinary star, but by a black hole feasting on the gas around it, and radiating away the resulting energy as heat and light. This matters enormously for our story, because it connects directly back to the too big, too early problem. In 2024, JWST observed a black hole from roughly 1.5 billion years after the Big Bang that appeared to be feeding on surrounding matter at an extraordinary rate, around 40 times what astronomers call the Eddington limit, the theoretical maximum rate at which a black hole is normally expected to be able to steadily consume material without blowing itself apart from the radiation pressure. If black holes in the very early universe were capable of feeding this aggressively and this efficiently, it offers a plausible route for supermassive black holes, and the massive galaxies that grow up around them, to reach enormous size far faster than anyone expected. This has revived and strengthened an older idea called the direct collapse black hole hypothesis. The traditional story of black hole formation goes like this: massive stars die, collapse into relatively small, stellar mass, black holes, and then those black holes slowly grow over billions of years by merging with others and steadily consuming gas. But if that were the only pathway available, there simply hasn't been enough cosmic time for black holes to reach the billion solar mass scale we're now seeing in the early universe. The direct collapse hypothesis proposes an alternative shortcut. Under the right conditions, massive clouds of primordial gas could have collapsed directly into a large, seed, black hole, skipping the intermediate step of forming an ordinary star first. A big black hole born big, rather than one that had to laboriously grow into that size over billions of years. It's important to be precise about where this idea currently stands. Direct collapse black holes remain a hypothesis under active investigation, not a confirmed fact. Researchers are still debating exactly what physical conditions would allow a gas cloud to collapse this way instead of fragmenting into ordinary stars, as gas clouds normally do. But the observational pressure supporting some version of this head start scenario has been building steadily, driven directly by JWST's discovery of black holes that appear far too massive, far too soon. If it holds up, it offers one of the most elegant solutions to our central mystery: massive black holes acting as gravitational anchors, kickstarting galaxy growth around them far earlier and far faster than the slow, patient, star-by-star model ever allowed for. It's also worth noting that the debate around little red dots is far from closed. There's still a competing, stellar-only, camp of researchers who argue that at least some of these compact red objects could be explained by extremely dense, dusty pockets of ordinary star formation, rather than black holes at all. Dust absorbs and re-emits light in ways that can mimic some of the same reddening signatures. Distinguishing between the two scenarios requires painstakingly detailed spectroscopy, teasing apart faint emission lines that reveal whether the light is coming from the churn of gas around a black hole, or from the combined glow of countless young stars. As of the most recent studies, the balance of evidence has been tilting more toward the black hole-powered explanation for the majority of these objects, but researchers are careful to note that little red dots are likely not a single, uniform population. Some may be black holes, some may be dense young galaxies, and some may be a hybrid of both, coexisting inside the same tiny patch of sky. What makes this scientifically satisfying, rather than just strange, is how well it dovetails with the too big, too early galaxy problem from earlier. If a subset of these early massive galaxies really do have an overmassive black hole embedded at their core, one that formed through direct collapse and then grew explosively through super-Eddington accretion, that black hole's gravity and energetic feedback could have played a genuine role in accelerating star formation in the surrounding gas, effectively giving certain galaxies a running head start. It's not a complete, unified answer to everything JWST has found. But it's one of the more physically grounded pieces of the puzzle currently on the table, backed by an accelerating number of spectroscopically confirmed detections, rather than speculation alone. So where does all of this actually leave us? It's tempting, especially for a story like this, to reach for the most dramatic possible conclusion, that the Big Bang itself is being disproven, that everything we know is a lie. That's not an honest description of where the science actually stands, and it's worth resisting that urge, because the real picture is more interesting than the exaggerated one. The Big Bang model itself, the basic idea that the universe began in an extremely hot, dense state roughly 13.8 billion years ago and has been expanding and cooling ever since, remains on incredibly solid ground, backed by multiple independent and completely unrelated lines of evidence, from the cosmic microwave background to the observed abundances of light elements like hydrogen and helium. JWST's discoveries are not threatening that foundation. What is genuinely being rewritten is something more specific, and arguably just as fascinating: our understanding of exactly how fast structure was able to form in the universe's earliest chapter, and what physical processes were operating in that first crucial second, and the few hundred million years that followed it. That's not a small correction, and it's not a footnote. It's a real, active, ongoing scientific debate playing out in real time, with the world's best telescope providing new evidence practically every few months. A handful of more speculative alternative ideas do exist on the far edges of this conversation, proposals like cyclic or bounce cosmologies, which suggest our universe's Big Bang might not have been an absolute beginning, but rather one phase in a repeating or transitional cosmic cycle. It's worth being upfront that these ideas remain highly speculative and are not currently supported by the kind of strong, direct observational evidence that the mainstream early dark energy and black hole seed explanations have. They're part of the broader conversation happening at the edges of theoretical cosmology, but they are not where the scientific consensus is heading right now, and it would be misleading to suggest otherwise. What's actually happening, in the most accurate sense, is this: astronomers built an extraordinary new instrument, pointed it at the oldest light in the observable universe, and found that the universe grew up faster than expected. Galaxies matured earlier. Black holes swelled larger, sooner. The neat, patient timeline of slow structure formation is being replaced by something more chaotic, more energetic, and frankly more exciting, a young universe that was far more vigorous and far more precocious than the models of just a few years ago ever predicted. Multiple major observing programs are continuing to push this frontier even further, hunting for still older, still more distant galaxies, while theorists refine their models of early dark energy, bursty star formation, and black hole seeding, to see which combination, if any single one, or some blend of several, actually accounts for everything JWST is showing us. This is genuinely unresolved. Nobody currently has the full answer. And that, more than any single galaxy or black hole, is the real headline here. We are living through one of those rare windows in science where the data is arriving faster than the theory can keep up with it, where the universe itself is handing astronomers a puzzle nobody fully expected, drawn from a period of cosmic history nobody could even see clearly until just a few years ago. The first second of time hasn't been proven a lie. But it has become, once again, one of the most genuinely open questions in all of physics, and thanks to JWST, we finally have the data to start asking it properly. If you found this breakdown of JWST's early universe discoveries interesting, the real research behind it, from the little red dots to the early dark energy debate, is still unfolding month by month, so consider this a snapshot of where the science stands right now, not the final word.